cross-sectional area or the length of the neck that separates the two black holes, and the entanglement entropy that's associated with the two actual black holes as they're entangled, as computed using something like the Fubini-Study metric, or the Fisher information metric, or the Burroughs metric, or something like that. So there are a bunch of kind of quantitative conjectures that have been made about how those two things might be related. One thing I realized a while ago was that we should be able to test this explicitly in the context of our models, because we now have, thanks to these, thanks to both the numerical relativity stuff and the sprinkling stuff that Stephen mentioned earlier on in the live stream, we can construct explicit examples of the Einstein-Rosen metric, and then we can evolve them as we can evolve those metrics as multi-way systems. And we can actually see what, essentially what the entanglement entropies are, because, in the context of our models, entanglement entropies are given essentially by branch-like separations. So we can construct the metric with a particular, classical geometry, and then we can look at the associated branch-like separations that would exist in the multi-way evolution, and we can just compare numerically how, those two quantities. And actually, if I hang on, maybe I can show an example in, yes, okay, in this notebook. So if I just quickly share and show, sorry, this thing here. So here are examples of these Einstein-Rosen bridges. So these are causal graphs that we've explicitly constructed so as to be able to, so that in the continuum limit, they will satisfy the continuum Einstein-Rosen geometry. And you'll see that I've configured them so that they have varying neck lengths, bridge lengths, and varying cross-sectional areas of the neck. And what I've done up here is plot, okay, so in orange is the theoretical prediction of the relationship between the cross-sectional area of the neck, which is on the x-axis here, and the entanglement entropy that's associated with the separation between the two between the two Schwarzschild metrics on either end. And so that relationship is shown in orange. And then in blue here, you can see the numerically computed relationship between those quantities in the context of our models. You'll see there's quite a lot of noise because of the fact that these are intrinsically sort of randomly generated metrics. These metrics are constructed by basically doing uniform Poisson sampling over a Lorentzian manifold. But if we took limits of arbitrarily large numbers of samples, then the standard deviation here would go dramatically down. But you can definitely see that there is a pretty good correspondence between the theoretical prediction of the ER equals EPR conjecture and the actual relationship between the space-time geometry and the branch time geometry that we compute from our models. So the hope is that we'll be able to validate a few more of these kind of more quantitative conjectures that come out of the holographic principle and ADS-CFT correspondence, and that will help us kind of make concrete this general idea that there is a duality between branch time geometry and space-time geometry. Now, we're sort of limited in a sense by how effectively we can do that because we still don't really have a complete sort of coordinatization theorem for branchial space. We understand coordinatization of physical space much better than we understand coordinatization of branchial space. So in some sense, we're limited by that restriction. But something like the ER equals EPR conjecture is nice because it's a result that we can derive purely, essentially looking only at the combinatorial geometry without having to care about how it actually gets coordinatized and embedded. So we're hoping to be able to investigate a few more of those kinds of results to make more tangible connections with things like ADS-CFT in the near future.